Alright, hello everyone. I'm doing Google Kickstart round D, and yeah, I know a lot of people on YouTube have been winning these things, but I don't think I can really compete against them, so I'm actually going to try to solve these problems at a slightly slower pace, but narrating as I go, and even writing out some proof to provide rigor to my solutions. Alright, so the scoreboard is empty. Who will solve something first? Probably not me, but that's okay. Yeah, it seems like we have 4 problems here. Record breaker, Allen piano, beauty of tree, locked doors. I'll try to get through all of them, and I'll post bookmarks in the YouTube description. So, number 1, record breaker, the 12-point problem. It's about our friend Isiana. Here, I'll make the font a bit bigger for the viewers. So yeah, we have a theme park, n days, and the number of visitors on each day is v. And we want to count the record-breaking days, which is basically the mountain numbers, where vi is greater than either of its... oh no, it's a new max, and it's greater than its successor. So yeah, let's go ahead and write the code for this. And I don't think there's too much to explain here. Let's just call it we'll keep track of the running max, and we'll also check if we're greater than a max. And yeah, actually I want to iterate. I'm going to go like this. So if vi is greater than max, then I'm going to set the max to its value. And if vi is further greater than vi plus 1, or as equal to the end, we're going to plus to our answer. Rename to ans because it's what it is. And yeah, my template should take care of all the formatting of the input and output. So no, sorry, this is vi. So yeah, let's go ahead and run this code. And yeah, I'll explain a bit of my thought process as I make the submission. I mean, there's really not too much to explain. We just kept track of the running max because it's kind of the criteria for whether it's record breaking or not. And then we compare with the next day, unless it's the last day, which is why we have this kind of or condition here. And cool, we passed the test cases, so we can move on to the next problem. Allen piano, an 18-pointer. 18 points, so that's a bit more than the previous one. We should expect it to be slightly more involved, but not by too much. Cool, so an alien. 4 keys. Okay, so it's kind of similar to the previous problem. And we're just looking at a sequence and the relative values. How often will I have to break its rules? Interesting. Because yeah, if you have like a descending sequence of 5 notes, there's no way to map it to 4 numbers. And yeah, we want the minimum number of times you'll have to break the rules. Yeah, that's actually a pretty difficult problem, and I don't immediately see a clean solution. So all I can think of is just keep track of the range of notes that you have, and just shorten the range or move the range for each number you encounter. So A, B, C, D, yeah, I can't really think of anything else, so I'm just going to go ahead and implement that. And I'll try to explain it a bit more as I go. Here, I'll do it like this. where I read in value. And I compare it with its previous. So here's the state I'm tracking. We're going to track the lowest and the highest possible notes. So low 1 is A, 2 is B, 3 is C, and 4 is D. And anything between in the closed interval low high is a possible note that prev could have been. Or it's unclear if it's prev. The current note may be. So yeah, if x is less than prev, that means you have to go down. So let's subtract both of these, because no matter where you were, you're going to shift down by 1. And do a similar thing if you're greater. And now we do some boundary checks. So make sure low is still within the bounds. Same with high. And same with the other end. And finally, check if we actually have an empty interval, which is definitely possible. Well, maybe we want to do that. Maybe we don't actually want this. So if low is greater than high, then reset and add 1 to our penalty. And that's kind of where the magic all happens. Because yeah, once we've discovered that low is greater than high, that means there's no valid answer. There's no valid note to assign to the ith note. So that means we have to break our rules, but once we have broken our rules, that means we can be anywhere again. So yeah, I don't actually know if this will work exactly, but I think, there's a good chance. And if it does, we can go ahead and submit that and just hope for the best. Yeah, I'm honestly not sure if this will pass, but what's life without a little fun? And yeah, some more little tricks that I glossed over. I skip the first number, but I do track it in prev. Just because the first number is never going to really cause issues for us. You can start anywhere you want. I also skipped a case where x equals prev. Don't do anything. Okay, so it turns out we got a wrong answer. That's kind of disappointing. Let's see if we can figure out why. Yeah, I don't know what I did wrong. That's kind of sad, but let's just stare at the code a bit. Maybe we're doing something silly here. Right, so one thing I'm noticing here is actually high should just be equal to 4 here, and low should just be 1. That's kind of an oversight I made, not realizing, like, if you're going down, you can actually go as far down as you want. The only thing that does matter is where your upper bound is. So yeah, this would have gotten affected, for example, by sequence. Let's say the sequence is like 5, 4, 3, 2, 5, 4, 3, 2, 1. This would have broken the code because once you get to 2, our range is like low and high are both equal to 1 at this point. And when you see the number 5, and like what you're supposed to do is you're supposed to put like the note D, the highest note. However, my code would have just put the note B, so that would have been incorrect. Yeah, I kind of didn't realize you could jump. But it is fitting, because that's kind of how I would sing all these things anyway. I would just, if the note has gone higher, I would just go up one step. Lower, I'd go down one step. I don't really distinguish between any intervals. And no, you don't want to hear me sing. Cool. So this next problem, 22-point problem, got a tree. We have a rooted tree with n nodes, and okay, it's ordered such that parents have smaller labels than their children. So 1 is the root. And yeah, we want to, that's what she's doing. She paints a random node's path to root. And then Bilva does this, every 8th node and every bth node. Interesting. Okay. Oh, expected beauty of the tree. Interesting. Okay. So the way I would solve this problem is kind of flip it. So consider every node and compute the probability that it's painted. And the way we do that is kind of look at its subtree. You know the deal. Just for each tree, you have to, what do we have to do? Compute the number of children at each level for each subtree. So that, let's see, for up to 5 cases, and it's like that. For all other cases, and it's like that. Okay. Geez, how do you do this? I think we might need to do some fancy merging of subtrees, smaller into larger. Though I would hate to have to write that code. There must be an easier way. Interesting. Okay, so here's what I got. Compute jump pointers, which is the 2 to the kth ancestor of every node. Use that to compute the 8th ancestor and the bth ancestor of every node. And this is like, these graphs are also graphs. They're forests now, because some nodes near the top don't have parents, don't have 8th parents. And then I realize that I'm saying 8th. What I mean, I'll write it out. It's not the number 8. So compute the 8th parent of every node. You can do via jump pointers. This defines a forest. In this forest, compute size of subtree for each node. Call it size, or let's call it size. Then probability that player A will paint node I is equal to size I over n. And then we just sum size I over n over whole I. Except what we want to do is that complementary counting stuff. N minus size 2 I over n. to get EV painted nodes. Same for B, size 2. And yeah, I don't know if there's an easier way to do this. I'm kind of surprised that they would want us to use jump pointers because this is only a 22-point problem, but whatever, let's just do it. So we're gonna actually do some some fancy stuff. So get vals, or let's call it probabilities. Yeah, get probs. We'll take in the graph. Let's take in the value A, and it'll return a vector of doubles. But the shared memory will be the graph. So the graph is represented as a parent array. And yeah, we'll parameterize this as like X or something, just so we avoid namespace variable name clashes. So let's read in our array. How does this work? And, cn par I minus par I, right? Because our nodes are 1 indexed, but we want them to be 0 indexed. The way the input works is the parent of node I plus 1, right? Yeah, so we start from 1, okay, should work. So yeah, the way we get to probabilities, here we compute jump pointers. We compute them up here. And how many jump pointers will we need? We'll just call that uppercase height, h. Okay. So the way this will work is while when shift left h is less than or equal to, no, it's just less than n, just increment h. Okay. Technically h can start at 0. We can be a bit cautious there, even though it shouldn't matter. Okay, so why does it not like this? Oh, equals. So yeah, vector double res vector int count and vector. Let's just iterate from bottom up. So let's also do get par int no cur int up. Up is how many nodes you want to climb up. And the way we'll do that is, oh, maybe I should have done one indexing. Never too late. Never too late. Yeah. So we're officially one index now. Yeah. So good thing we did less than or equal to n here. Cool. So if up is on in bit I, then we want to go up. Jump. And then we just return cur. Cool. So let's actually compute this array. So yeah, 0 is going to be the terminal, it's going to be the fake node. What that means is everything will end at 0. It's actually a cycle. 0 has a self pointer. Let's do this again. Except here, we're going to use the 8th layer to compute the h plus 1th layer, like that. And that will give us what we want. If you're not familiar with jump parents, basically jump I h equals 2 to the h parent of I, 0 if it exceeds the tree. So yeah, it's a pretty cool trick. What am I doing here? Why doesn't it like my code? Oh, because I'm missing my variable name. All right, so get pair is not used, get probs is not used. Well, just do weights. So we're gonna do this. Count of get pair of I, comma x plus equals count of I. But first, increment 1, because you might land on yourself. And I think this just works, so we'll just set the value of the result to be, well, we don't need, we'll just res divide by n. And cool, we're almost done. Now we just have to run the code. So, double, what do we call them? Let's call them P1, P2. And one of them is A, the other one is B. Keep writing props, doing too much front-end coding. Okay, and now we just want to add up all the values of, let's call it prob, where prob was 1 minus P1. And this is the kind of complementary counting to get probability. Node I is painted. And yep, this is 1 indexed. And let's print that out. So yeah, I have not really been checking my code for bugs, but I suppose that's why we're going to run the code. Okay, no more yellow arrows, so that means no lit warnings. Do I need to do anything special? Hopefully not. Yeah, it says A is less than or equal to N, so I'm actually kind of concerned, but not that concerned. Because, like, that doesn't really make sense. Why would it be equal to N? And everything's just going to be 1 over N. Okay, answers are all wrong. That's not what I was hoping for, but let's print out some values and see if that helps. So case 1, I haven't actually looked at this, but this is the graph, and what is my, ooh, some crazy stuff is going on. Got a malloc free thingy. That's not good at all. I probably messed up that. So my array was too small. Answers are still wrong. Good. Yeah, these numbers seem a bit big to me. Shouldn't n be 8? So shouldn't these all? Let's just print out some basics. What is the parent of 1? And what is the second parent of 1? Of 8? And what is the third parent of 8? I'm expecting this to be 4, 3, and 1. In the first case, at least. Hey, why isn't it printing out the things I wanted to print out? Here we are. Okay, so it's all incorrect. We can debug this. So, aha, because this should be par of I. Everything is right now incorrectly linked together. But yeah, that's a classic mistake. Okay, things are not that much better. Yeah, I'm at a loss. Maybe this should be one, but and there's never going to be 0, so doesn't really matter. Okay, so let's take a look at the first case again. 431. That's exactly right. So case number 3. Well, 8 doesn't exist, so that's actually normal. If I delete these lines, it should just stop doing that. And our numbers are still a bit off, but we're getting there. What is it asking for anyway? Oh, so you don't actually... No, you do paint every 8th node. So what's going on? P1. Okay, yeah, this is definitely wrong, because you're always going to paint the top node. And yeah, this is all wrong. Let's see if we can fix that. So count. Oh, because we started at n-1. That's my fault. We should have started at n. I always get confused by 1 indexing and 0 indexing. Switching between them doesn't really work that well for me. But yeah, we're passing the samples now. That took a while, but hopefully it was worth it. And just to kind of rehash the big picture again, what we did was we took this tree, we broke the problem into 2 separate problems, player A and player B. We broke them up into 2 separate problems so that we could later combine the subproblem results and get our final answer. And the way we combine them is using linearity of expectation. The expected number of nodes that are colored is the sum of the probabilities that each individual node is colored. And the probability that a node is colored, well, you can compute the probability that it isn't colored in each of the subproblems, and those multiply because two subproblems are independent. So hopefully that makes sense. We passed the samples, so it did make sense to the computer at least. If you have any questions, please, drop a comment below, and I'll draw a nice little diagram. So on to the last problem, locked doors, 38 pointer. Maybe we can do a quick scoreboard check. Anyone finished yet? No. Where are we at? We are in 10th place. So, there's still a small chance that we win this whole thing, though it's looking quite unlikely. Look at our penalty, it's like double this guy's. What are we doing? Who knows? It's okay. Let's finish this problem. So, the 38-point problem, the hardest problem on this contest. Let's see how we fare. And it's about our friend Bengals. You know that this is an anagram of Bengals, which I thought I would Google. Yeah, it's an American football team. Okay, this is random tab I have open. Okay, so there's a museum with n rooms, difficulty level for each room, or for each door, I'm sorry. So it's a sequence of rooms from left to right. No 2 doors have the same difficulty, and yeah, there's n-1 difficulties from 0 to n-2. Take a picture. Okay, I don't really understand. Isn't it just she picks a direction, goes all the way, and then comes back and goes all the way? Huh, no, that's not quite right. Oh, no, she might just go back and forth, huh? We need to look at the samples. So this is the first case. The 4 queries. How does this work? N, Q, 2 lines, S and K. What's S and K? Okay, S is start and K is number of pictures. So start here. 0, 1, 2, 3, 4. No. Okay. Let's draw a diagram. Cool. So here's our diagram. It's a bit bigger. Cool. So in the first case, we actually have some 4 rooms. Or 5 rooms. We started out over here. This is 3, so this is room 3, and we go 4 turns. So first we go to this room. Here, let me draw this underneath. And then we come back. So we go back and forth 4 times. Okay, 5, 3, 5, 2. That doesn't seem right. So maybe I'm misreading the problem. Oh, so once the door is unlocked, it remains unlocked? Okay, I don't really understand. Three, 2, 3, 2, 4, 5. Oh, I get it. Okay. I'm so silly. So the 2 doors are that they refer to over here, like available, that's just, it doesn't mean they're adjacent to the room she's in. It's just like that she can reach without encountering any locked doors. Okay, so that makes a lot more sense now. I still don't know how to solve the problem, but at least I know what it's asking. So that's improvement. So yeah, I think the trickiness here is that k can be quite large, so we can't just directly simulate it, because that would take k times q time, which, it's like 10 to the 10 per test case, and there's like 100 test cases. That's not going to fly. So what we can do is do some kind of DP, perhaps. Some kind of state compression, so that we can take advantage of overlap between subproblems. Yeah, dynamic programming, it's a great way to trade memory for speed, and it's always useful in times like these, when you have n squared possible states. Well, hopefully fewer, but when you have a lot of states and they kind of transition back and forth, but you kind of keep ending in the same situation as ones you've seen before. So yeah, let's try to formulate this problem as a DP. Stack this a bit more. So if you start here, you're just going to take everything until you take 30. And chances are, if you start here, that's kind of the same situation. Yeah, so you're kind of like, if you're here, you're just going to go left until you hit something bigger than 30, and you're going to go right until you hit something bigger than that. And like, that just means for each number, you have to know it's, for each I, you want to know that the closest neighbor it has that's greater than it in either direction. And that'll kind of help you do these transitions faster. That's still not enough to solve the problem. That just simplifies things a bit, what do we have left to do? At any point in time, your state is going to be an interval from A to B where, well, the key states are when you change direction. And any intermediates should be fairly straightforward. Okay, so maybe we can draw a little diagram. So say you have this big array, and at any point in time, your state is going to be it's going to be some range. And let's say this guy is bigger. So that means your next move is just going to be opening doors on the right until this guy becomes bigger. Let's say this was like a 1, this is a 3, and you kept looking at numbers less than 1, like 2, and then you hit a big number, 6. Now you're going to start moving this way until you hit like an even bigger number. So we just need a way to do these efficiently, but more importantly, like, is it possible for there to be a bigger number in here? Like, how can it be? It's not possible. So in particular, the only, like, there's no way you can have things that are bigger than both your endpoints. So that really limits the number of valid states that we're dealing with here to like, I think O of n. Sorry, not only is it O of n, like these are smaller than either A and B. You know what? I don't think I can explain myself, but there's only O of n states. There's only O of n states where A and B greater than all C between A and B. Between positionally. So yeah, the endpoints are also both the maxima. There's not that many arrays like that. There's not that many subarrays like that. I just don't know what to say. Yeah. Every element is the left endpoint of at exactly, or is it at most? I don't know. At most? Is that true? It's it's left endpoint and it's smaller at most once. And that kind of accounts for everything. So, then. Now the question is, oh, someone's almost done. How do we implement this? I'm sorry, my computer just froze for a sec. But what we're going to do is, I don't know what we're going to do. Like, these intervals kind of form a tree, don't they? And we're looking for an answer that we know the size of. So I'm wondering if we can just do a jump pointer kind of trick. So let's draw this out. So maybe you have like 1, 9 here, and it'll have children like 1, 8, and this will have children. I don't really understand how the whole children thing works, but eventually you'll have a comma, a plus 1, maybe? Because that is always a valid thing, right? A comma, a plus 1. Just no 2 equal, yeah. So we just want to binary search up your list of parents until you find something, the first thing that is bigger. So now you just have a child and a parent. And at that point, you can probably figure out the intermediate stage that has exactly the right number of elements. Yeah. Something tells me that I could be doing this a lot smarter. Like, there's gotta be like an end root n solution where for each node you compute its root nth parent. Like, how could that not be the right answer? Like, yeah, it seems like that would work too. So I'm gonna go ahead and implement that instead. Yeah. Root n log n. Yeah, that's probably fine. Maybe I should use unordered set just to be safe. Nah. Okay. So a node is a pair, a B. Parent of a node is A prime, B prime. Well, compute root n parents of every node, or let's just say memorize root n parents. Yeah. So how do we do that? How do we do that? Hold up. Is this going to TLE? Maybe. Maybe. Is it going to TLE? That's the question. I can't really reason about this. I really just want to try it. I think it might TLE. Like consider just 1, 2, 3, 4, 5, 6, 7, 8, 9. There's just so many nodes that you have to compute the root and parent of, unless you can do it quickly. Yeah, that's kind of unfortunate that it comes to this. Oh, I really don't know what I'm thinking right now. There's n squared nodes in this graph, but only n of them actually matter. What's the best way to make use of that information? I could just directly compute the nodes that matter, and also stack that on top of the root n thing for all the nodes that matter. Yeah, that sounds like a good idea. Okay. Yeah, I think this might work. But climbing up root n at a time, how does one even do that? Like, that still sounds kind of tedious. So you still need some kind of jumping. Oh, I really want to just submit something. Okay, let's think this through a bit. Okay, I think I have a better understanding of the problem now. Hmm. Something like that, right? Right, okay. So yeah, k is 2 and pair of s is s plus 1. So maybe this is a greater than equal. Okay. We're going to subtract 1 from k at a time. Okay. Okay. So there's n rooms, right? We're going to do it like this. The length is how far right or left you go. Yeah, we're not actually going to subtract A, I'm sorry. Sorry, I know I haven't been very instructive. This is just kind of a hard problem. But here's what we're doing. We're saying we're reducing the problem by jumping S but not K. And that's kind of, very smart of me. Very impressed that I figured that out. This is actually just such a hard problem that I'm not sure I'm doing it correctly. Alright, so I have to compute pre-even next somehow. I don't even know. How do you do that? Whatever, I'll figure it out later. Finish writing the skeleton first. So this is using the same trick we just used last problem. My code is so bad. I don't know what I'm doing. I'm sorry. I'm too tired for this. I'm far too tired for this. I printed out 0302. Yeah, that can't possibly be right. Oh my god. Okay. So prev is a bunch of zeros. That seems reasonable. No, does it? I'm not sure it does. It should be ones. No, what am I doing? I had it fine. So why is it doing this? Prev should be one. Prev should be one. This is all wrong. Okay, well clearly I'm comparing it incorrectly here. Oh my god, yeah, what am I doing? Okay. So let's start with prev. No, let's start with next. Yeah, n minus 1. I can't solve this problem. Oh, I'm an idiot. I'm doing V instead of stack. What a bad bug to make. Okay. Seems like infinite looping. Because I'm doing, oh my god. Okay, I'm still getting everything wrong, but at least these numbers are looking a bit more reasonable. Okay, it seems like we're almost done, so just have to subtract one from S, try again. 4241. Great, great. I just have to add one here. See if it passes. It probably won't pass. I haven't checked any of my code. But if it somehow passes, that'd be really cool. Did it submit? Okay. Okay, so yeah, what's going on? What's going on here is I'm about to get like some kind of wrong answer. Failed to sample. 5352. Oh, U line instead of space. How silly of me. Okay. So what's going on here is I'm doing some crazy stuff, but here's the key. My answer is I want to get it so that this is my answer. It's either you go right by k minus 1 or you go left by k minus 1. Because it's always a continuous range. Always going to get to some endpoint and move right or move left. And you can actually compute for every node its next parent that has a wider range. Hey, look at that. So we passed. Let's take a look at our final standings. I think we got 13th. Okay, it's not bad at all. That was a very hard problem. I probably didn't do it the most efficient way, but hey, That's not a big deal. You know, if we didn't get that penalty, we'd be right around where we are anyway, so it's not a big deal. Maybe a difference of 3 places, 2 places. But yeah, I want to recap that last problem just because it was pretty tricky. I don't know how other people solved it. They probably did something a bit simpler because this is a lot of code. Especially this stuff is very sketchy. Like, I honestly don't know what I'm doing here. Like, this code, I'll write some. So yeah, step 1 is compute what side each door is of each room is closed. 0 means left is harder, 1 means right is harder. Step 2, create a vector to hold length of each room. Length is the number of rooms you will see if you start from room I before having to open the hard door. All right, so I just organized my thoughts on kind of how this program works. And yeah, thanks for sticking around if you're still watching, because this problem is a bit involved. But I think I think I figured it out. So the high level is, let me emphasize the end. We can build a graph over the rooms. So this way we can just defined in the question. The question is like they're querying S, comma K, right? What is the kth room that she'll take a picture in if she starts in the Sth room? We're just gonna use this problem statement wholesale because it's actually a pretty convenient formulation of the underlying problem. Which is like if you're in a room, what is the kth room in this room's range? And yeah, my observation is basically that for each room, you'll either go left or go right as your first move, and you'll go left or go right some number of times before you stop and turn around, right? And I think that's kind of the first observation most people would make when looking at this problem. And that actually captures the entire structure of the problem. Every node is characterized by a direction that you would go in if you're starting out from there, and a number of steps that you're going to take. However, the number of steps you can actually make the observation is equivalent to saying that this node has a parent. So let's look at our diagrams. Let's say you have a room, you have a bunch of doors, right? Like let's say there's a door of weight 10, door of weight 3, door of weight 7, door of weight 6. And let's say this is your room 0, 1, 2, 3, 4. So let's consider room number 2. Parent of 2 is going to be equal to 1. Let me make this bigger. What does that mean? That means if you're asking what is a third room, this means the third room you visit take a picture of, or yeah, picture of when starting in room 2 is the same as the third room. Take a picture of when starting in room 1. And true not just for third, but all k greater than len 2. And what was len of 2 again? Len of 2 is just 2. That's the number of rooms you'll visit on your first leg. So len 2 is 2. This is the number of rooms you'll visit before changing directions. Because remember, your first step is going to go here, breaking down this wall 3, and then you're going to go here, breaking down the 7 wall, then you're going to go here, and then only then will you go here. So yeah, len 2 is 2, par 2 is 1. I hope this makes sense. Parent of 2 equals 1 is kind of the key observation I made. It's like you can greatly simplify the problem or like I found a recurrence relation. So and the property of star, this gives us a nice recurrence relation. In other words, a way to reduce problems to subproblems. In this case, we're reducing a room, problem fk s comma k to f of par s k. Yeah. So yeah, once we make this realization, it's actually fairly simple to find the answer. You just keep going up your parents until you have someone whose length is large enough, but you want the first one. And to solve that, we used jump pointers, which is a pretty standard technique when working with trees. So yeah. And yeah, if you have questions, leave them in the comments below. I probably didn't do a perfect job of explaining this. I'll post some links to jump pointers. But I'm sure there's a good one on the internet already. Yeah, the first one looks like a pretty good one. Yeah, so I'll link this in the description as well. And let me see, is there anything else that I glossed over? No, I don't think so. I think everything was explained pretty clearly. So, yeah, thanks for watching. Hopefully next time I place a bit higher. So I'm pretty happy with how I did. As I said in the beginning, I'm not trying to win these competitions. I don't think I could have beaten this penalty time even if I were 100% focused, because, 41 minutes for 4 problems takes a lot of skill, and that's not something I really feel confident in my abilities for. Speed coding is just not easy. Here's the final scoreboard. You can see Eknerwala up there. Good job, Andrew. Yeah, wow, I'm really impressed by this guy. Beat Azu. He solved problem D in 19 minutes. Andrew solved in 18 minutes. This guy solved it in 21 minutes. This guy solved in 33 minutes. Wow. And I took 50 minutes. 47 minutes? Yeah, 47 minutes. Not a great penalty time. But we're still seeing more people trickle in with their submissions. Honestly, I don't know if I even did this in the simplest way. I probably didn't. Yeah, William did pretty well, 27 minutes for the last problem. Yeah, overall, how do I feel? I feel a bit disappointed that I didn't do better. Like, I was actually doing really well on the first 3 problems, despite commentating. I was ahead of most people, it seems. 27 minutes split, yeah, I was ahead of a lot of these people. The last problem really didn't go that well for me, though. Yeah. Yeah, I don't know the next time I'll be doing one of these, but if you liked it, please leave a comment below, and that'll help me know whether to keep doing any of these in the future.